Okay, let's continue our review for the Unit 1 lecture exam in astronomy. And you're not going to need to know anything about the false explanation for celestial mechanics being caused by planets eating their Jimmy Dean sausages. However, you definitely need to know about a guy by the name of Ptolemy, ancient Greek, 2,000 years ago, believed that the Earth was the center of the universe, geocentric universe. Okay, then later, about 1,500 years later, a guy by the name of Copernicus comes up with the idea that the sun is the center of the universe. Still not quite right, because it's saying that the sun is the center of the universe, and the sun is not even the center of our Milky Way galaxy. But it is true that our sun is the center of our solar system. Okay, then about 100 years after Copernicus is Galileo. You need to know about Galileo for two things. One is he observed the moons of Jupiter and noticed that since the moons were going around Jupiter, it would make sense that the Earth is going around the sun. But then he also noticed that Venus goes through phases, just like the moon. Sometimes Venus is extra bright, sometimes Venus is extra dark. And the only way that that can happen is if Venus is in orbit around the sun. Okay, then you got Kepler. So Kepler is a contemporary of Galileo, and he comes up with 3 laws of planetary motion. So his first law is that a planet is in orbit around a sun in the form of an ellipse. An ellipse has 2 focuses. There's nothing located at the other focus, but one of the focuses is where the sun is at, and then the planet is in orbit around that in the shape of an ellipse. Okay, his second law, equal areas in equal amounts of time. So that a planet will sweep out an equal area in the same amount of time. And this is because of conservation of angular momentum. So that's L is equal to mv r. So as a planet gets closer to the sun, r is getting smaller. So that means that v has to get bigger. So if in the same amount of time, if the velocity is faster, it can cover a larger distance. So that's the reason why over here it covers a larger distance in the same amount of time because it's going faster. Over here it doesn't cover very large distance because it's moving slower. But when you multiply the large r times this small distance here, it turns out to be the same as this small r multiplied by this big distance over here. Okay, then you got to know his third law of motion. So this one is a mathematical formula. It does not use metric units. So this is the period. So it's the time that it takes a planet to go around a star in years. So the unit for the period is in Earth years. But you got to square it. And then it's equal to the distance the planet is from the sun cubed. And this is going to be in astronomical units. So the unit for this one over here is going to be in Earth years, and then the unit for this one over here is going to be in astronomical units. So here is the kind of question I would like for you to be able to answer on the exam. If I tell you what the distance is, can you cube it? So in this case, 7 times 7 times 7 is 343. Okay, then you have to take the square root of it. So in order to get rid of the square, you got to take the square root. So the square root of 343 is 19, and then the unit is in years, so you'd say 19 years. So that's what I would expect you to be able to do. Okay, then along comes Sir Isaac Newton. And so one of the things that Newton figures out is the energy, the potential energy caused by gravity. You do not need to know it for the exam, but what you ought to notice is it depends on the masses of the two objects that are interacting with each other, and it also depends on the distance in between them. So what does gravitational potential energy depend on? So it depends on the mass of the rocket, depends on what it's in orbit around, and then what's the distance between the two. Okay, then all objects have both potential and kinetic energy. So we mentioned before that E for the energy of an object is the sum of its kinetic energy plus its potential energy. So this depends on how fast it's going. So kinetic energy depends on the speed of the object. But the potential energy depends on distance. So the distance between the objects. And so the orbit of an object around a planet or a star is going to ultimately depend on its speed. So let's first assume it doesn't have enough speed. You got a rocket, you shoot it off the surface of the Earth, but the rocket doesn't have enough speed. It's going to crash back onto the Earth. So it's going to actually have an elliptical orbit. It's just that the Earth is getting in the way. So if this is the Earth, and then you launch your rocket, it tries to escape, but it can't. So it crashes back into the Earth. But actually, if you could continue to follow it, it would go around the core of the Earth, and then it would come back out of the ground again. So that's an elliptical orbit. Okay, let's give it more speed. So if you give it more speed, it's possible that that object could completely go around the Earth for a certain speed. It's making a circle, so the velocity is called the circular speed. So at a certain speed, an object will go in a circle around the Earth. Now, if it goes even faster, now what can happen is it turns into an ellipse. But at a certain speed, the orbit is going to snap. And so then it's going to go into a parabolic orbit. So if at a critical speed, it goes into this parabolic orbit, the velocity is going to be the escape velocity. Sorry about that, you can't see that. So escape velocity. And then you can even go faster. So if you go faster than the escape velocity, it has yet another orbit, and that's called a hyperbola. So this one is the hyperbolic orbit. This one here is the parabolic orbit, and then this one here is the elliptical orbit. Two L's. Okay? So those are the different kinds of orbits that an object can have, and it all comes down to the speed. So if it doesn't have enough speed, it's got the elliptical orbit. If it's got just the right speed and can escape, it has escape velocity. And then if it goes even faster than that, then it has this hyperbolic orbit. So, there you go. And there are actually formulas for being able to calculate the circular speed and the escape speed. You're not going to do it, but there's the two formulas for actually how to calculate what speed you have to be going at. Okay, then another thing that Sir Isaac Newton came up with was he modified this formula. So the original formula that Kepler came up with was the period squared is equal to the distance cubed. Well, one of the major things that Sir Isaac Newton added was it also depended on the mass, the total mass. So the mass of the star plus the mass of the planet that's in orbit around it, so that's the total mass, so m sub t. So he found that this is actually the correct formula. Now, if you want to make this formula metric, then you also have to include the big G thing and the 4 pi squared. But you're not actually going to calculate the period in metric units. Okay, one more thing that Sir Isaac Newton came up with was the concept of center of mass. So I want you to think about a teeter-totter. So there's a teeter-totter, and then if you've got a very large person over here, where do you need to put a little person in order to balance it? So you need to have the little person out here. So notice that you got a big person multiplied by a small distance is the same as a small person multiplied by a big person, big distance here. And this thing here, the pivot point, is going to be the center of mass. It's where all the mass would appear to be concentrated at. So it's the pivot point. So imagine that we could take this teeter-totter and make it rotate like this. Then this would be the star, and then this would be the planet, and then this would be the center of mass for the solar system. We can actually calculate the center of mass using that formula up there, but we're not going to do it. I just want you to know what is the concept of what is center of mass. And the idea that both the star and the planet are actually both in orbit around their common center of mass. All right, let's take a break, and when we come back, we're going to talk about relativity.